Alright, by now you have probably noticed that there's none of the static that you usually observe at the start of my video, and my voice also has a slightly better quality to it, and that's because I've finally gotten a proper mic to record. So hopefully enough, this will mean that my videos will be slightly more pleasant for you to watch. And if you're interested in knowing the exact difference between them, let me just switch over to the headphones right now. This is the headphones. I know it is extremely bad compared to what you were listening to just a moment ago, so let me just switch back. So this is the mic. And so with that out of the way, let's talk about today's topic, and that is the equation of continuity and Bernoulli's theorem in the context of fluids. Now, generally speaking, most of the theorems and laws that you have in physics are based on a few fundamental postulates, or well, laws in general anyway. So these include laws like the conservation of energy, the conservation of mass, and the conservation of momentum, and so on and so forth. And so in the context of fluids, the laws that we are most concerned with include the law of conservation of mass, which we will use to derive the equation of continuity, and secondly, the law of conservation of energy, which we will use to derive the Bernoulli theorem. And now if you have also done current electricity, then you may find analogies to these laws, and the first analogy will be using the conservation of charge. That is, the Kirchhoff's laws are actually based on the conservation of charge and the conservation of energy. So if you wanted to draw an analogy of sorts, then you could find that as an analogy. That is, Kirchhoff's current law is based on is similar to the equation of continuity, and Kirchhoff's loop rule is similar to Bernoulli's theorem in the fact that they both use the conservation of energy. Alright, so let's begin. First, we're going to consider a cylindrical tube of varying cross section. Alright, so this is a tube, and let me draw it like this to indicate the fact that this is in fact a varying cross section. So we're going to say that this cross section over here is actually A1, right? And this cross section over here is actually A2. In general, this can apply for any cross section any cross section within this tube, but for simplicity's sake, we'll consider cross sections at two ends of a tube. And so that's A1 and A2, and we're going to assume that fluid at this point is going at the speed V1, and fluid at this point is going with the speed V2. And we are also going to let there be a fluid of, say, density rho within this, and we're also going to assume that this is an incompressible fluid, that is, its volume cannot be changed. That is actually critical to this derivation over here. So we're going to let it be a fluid of density rho. So like I said, this is based on the conservation of mass. So we're going to say that the amount of mass coming in through this tube over here has to be equal to the amount of mass going out of this tube over here. However, that alone is not sufficient. What we're also going to say is the rate of mass of the fluid entering this tube is going to be equal to the rate of the mass of the fluid exiting this tube. So we can say d of m1, let this be m1 over here, dm1 by dt is equal to dm2 by dt, which is the amount of fluid that is exiting from this cross section over here. So again, we can write m1 as rho v1, and we can write m2 as rho v2. And in fact, we can get rid of the subscripts over here because, okay, I'll let them be there. It's okay. So in general, then we can actually write this as rho times d of v1 by dt times rho of dv2 by dt. And now this is actually capital V. This is not the small v over here. This is actually capital V, and this indicates the volume because I've written m as rho times v. That is, m is equal to the density times the volume. So this is what I'm doing over here. So since the density of the fluid is constant, I've taken it out of the equation, and I've actually written this as dv1 by dt is equal to rho times dv2 by dt. So I can just cut the densities over here, and I can simply talk about the rate of change of volume. That is actually what we want over here. So this tells us that not only is the mass constant, but also the volume of fluid that is entering over here and exiting over here. Alright, so we're going to write an expression for volume over here. I'm going to say that the volume that is entering or exiting a given cross section is equal to the area of the cross section, no matter what it is, times the length of that cross section. So over here, if I have suppose a circular cross section, and I'm going to let it be of say cross section A, and suppose it has a length L over here that I'm considering. So this over here would be, suppose the amount of fluid contained over here would be the volume of this cross section, and that would also be the volume of the fluid contained within that cross section. So I'm going to write V is equal to AL. So V1 would actually be equal to say A into L1, A1 L1, and V2 would be equal to A2 L2. Alright. And so when I differentiate these with respect to time, I'm going to assume that for these infinitesimally small cross sections, the area of the cross section is going to be constant. So what's going to change would be, suppose if I differentiate d1 by dt, I can take area of the cross section as constant. So I can write this as a1 times dl1 by dt. And this is nothing but the velocity of the fluid through this cross section, right? So I can replace this and write this as a1 times v1. Similarly, I can do the same thing for dv2 by dt. That will actually be equal to, suppose this would actually be equal to e2 v2. All right. And so this equation can instead be written as a1 v1 is equal to a2 v2. And this is nothing but the equation of continuity. And that's pretty much it. And this equation holds true no matter what situation is, because it's based on a very fundamental principle, that is the conservation of mass. And so no matter what kind of forces that you have, what kind of forces are acting on the system, and no matter what kind of shape it is, especially because we only care about the actual area. It doesn't matter if it's suppose a cuboidal shape or a cylindrical shape, it'll still hold true. And so you can sort of draw a few conclusions. Suppose if the area of cross section is very small, then the velocity of the fluid through that region will most likely be quite high, and vice versa, that is if the area of cross section is very large, and therefore the velocity of the fluid through that same cross section will also be quite small. So that's pretty much all about the equation of continuity. And next we'll talk about Bernoulli's theorem. And of course, this equation does assume a few things, that is, the fluid has to be incompressible. Alright, so let's look at what would happen if the fluid was not incompressible. So you could decrease its volume by applying some pressure or force on its exterior. So what would happen is that its volume would change with time, and so would its density. And that means that when we're differentiating the mass over here, we would have to apply the product rule. So it would actually be rho dv by dt plus v times d rho by dt. And so and in that case, you would probably not get a very elegant expression. Like this expression is really elegant, like really simple. And so in general, like you would just be better off just applying the conservation of mass, since you would not get an equation of continuity per se. So moving on to the next topic, that is Bernoulli's theorem. Alright, so let's talk about Bernoulli's theorem or Bernoulli's equation, or well, Bernoulli's principle, whatever you want to call it. Generally speaking, like I've said before, it is nothing but a statement of the conservation of energy of the fluid system, that is the fluid and earth system. And so you might have seen various other conservation of energy system equations, that is for the mechanical energy of a system, that is mechanical energy of a system is given by half mv square, that is the mechanical energy of the kinetic energy of the body that is moving, plus its potential energy with respect to the earth, right? That is, if it's taken to a height h, then it has some potential energy with respect to an object on the ground. And so Bernoulli's theorem is nothing but a statement of the energy contained within a fluid, you could, if you want to call it that, but in terms of a fluid, obviously, because it's not going to be the same. So let me just state it over here to help you get an idea of what the principle actually is. It states that the sum of the pressure exerted by a fluid in all direction plus the kinetic energy per unit volume. So kinetic energy would be half mv square, but since this is per unit volume, I'm actually going to write this as half rho v square, where rho is the density and that is actually equal to mass by volume, right? So half rho v square plus rho g h is a constant. And so you will obviously see that there's this big difference between this and the conservation of energy for some, say, a particle that is moving along a line, right? And that is this term over here, and that is the term that talks about the pressure. And so to give you an idea of what I mean when I say pressure itself contains some energy, let me give an example here. So suppose this is a tank A, all right, and it is kept at a pressure, say, P naught, all right, and this is a tank B, and this is kept at a pressure 2 P naught. So what will happen is the fluid in this tank will actually flow to this tank until the pressures are equal. So we can think that pressure itself has some capacity to do work, and well, energy is nothing but the capacity to do work, yeah? And technically when I say pressure has energy associated with it, I mean, correctly speaking, I mean the pressure energy that is given by P times V. So if you were to multiply all these terms by the volume, you'd actually get terms that indicate energy itself, because all these terms have dimensions that are equal to energy by volume. So if you were to multiply, then you would get the actual energy terms, and the energy term for pressure energy is actually P times V. So with that out of the way, we'll actually look at how exactly we get this result. And we'll also look at some of the applications of these, because there are actually quite a few applications in the next video. So for this, to give a proof of this, I will draw again a tube of varying cross section, but in this case I'm also going to allow it to go over some height h to also indicate the fact that even when the gravitational potential energy associated with the fluid changes, this equation still holds. So this over here is going to be a tube. Wait, that looks like it has the same cross section, so let me just draw it again, and I'm going to make this tiny. And alright, so this over here is a tube of varying cross section. Over here I'm going to let it be A1, and over here I'm going to let it be A2. So over here you can think that the fluid is actually exerting a pressure in this direction. Although technically speaking the fluid is exerting a pressure equally in all directions, what we're actually concerned with over here is the pressure exerted in this direction. And the reason for that is there's most likely an external force over here that is pushing the fluid in this direction and doing work on it. So but what we're concerned in over here is the work done by the fluid, and that pressure is actually in this direction. Similarly, in this case, there's most likely an external force that is we can consider it to be, suppose, as atmospheric pressure. That is also an external force here. So over here the external force is trying to push the fluid in, trying to get it to stay inside. So in this case there's actually a pressure P2 being exerted by the fluid in this direction. Similarly, you can consider the velocity, say, v1 at this point, and the velocity v2 at this point, alright? And we're also going to consider, say, a volume of fluid that is being taken around this entire tube and being brought over here. And since it's incompressible, this volume is again going to remain the same. So with all of that in mind, and of course you also have to consider the heights over here, right? So I'm going to draw the ground over here. That's a very level ground. So this point over here is going to be at a height h1, and this point over here is actually going to be at a height h2, right? And so this will actually serve as the potential energy term. The velocity will help us determine the kinetic energy terms, and the pressure will help us determine the pressure energy terms. So with that, let us now write a general statement for the conservation of energy for this system. So if it was just say a particle moving, you would just have written the kinetic energy and potential energy, yeah? But over here we're also going to include a term that is for the work done by the pressure of the fluid. So what I'm going to say is work net plus delta K, that is the change in kinetic energy, plus say delta U or delta P, I like to use delta U, is equal to 0 because there are no other forces acting on this fluid over here. I did say that there was an external force, but that is actually well balanced, you could say, by the fluid. So there's no net external force acting on this fluid over here that will cause the energy of this fluid to change, because I've considered the fluid and the earth as the system. So the gravitational force is not an external force, but is in fact a force of the system. All right. So we have this statement over here. So we'll try and get the values for each of these terms, and then we'll evaluate and see what we get. So to get work net, we'll have to find the work done at either end. So the work done at the end one, let me just write an expression for that. Work done would actually be equal to F dot T, that is, this is both of them are vectors. So let this be some length L1 over here, and this will also be force L1. So this would actually be F1 dot L1, right? And so you can see that the pressure is over here, whereas the velocity is over here. This means that there is a displacement in this direction. So what this actually means is that work 1 is actually equal to minus F1 L1. But again, we're not actually concerned with the forces over here. When you're talking about fluids, we're most likely concerned about the pressure that they exert. So this can further be written as minus P1 times A1 L1. And this A1 L1 is nothing but the volume of the fluid, right? Similarly, at the other end, we can write a similar equation, except for this end, the force is in the same direction. That is, the fluid is exerting a pressure in this direction. So we can write F work 2 is equal to F2 dot L2. And this, when we do all of it, will actually evaluate to P2 into A2 L2, right? Because over here we'll actually have a positive sign, and this will be equal to 1. So we can write work net, right, is equal to work 1 plus work 2. So I'll just skip writing that, and that will actually be equal to P2 minus P1 times the volume of the fluid. So that is our first term that we've gotten over there. Now delta K is pretty easy to write. It's simply the difference in kinetic energy of the fluid between those 2 points. But here we need an expression in terms of densities, right? So instead of writing the mass, that is, instead of writing half mv square, what I'm going to do is I'm going to write half rho times the volume into v square, that is the velocity. So let me write half rho v times v2 square minus half rho v into v1 square. I don't know if I've mentioned this, but the volume over here is same because again this is an incompressible fluid that we're talking about. So we can take half rho v outside of the bracket, that is, we can take it common, and we can write this as v2 square minus v1 square. And lastly, for an expression of potential energy, gravitational potential energy, we can write mgh2 minus mgh1. So this will actually be equal to mg into h2 minus h1. Alright, so now that we have all of our terms, let us actually put them into the equation. So we can write this as p into, no, my bad, it's not p. It's p2 minus p1 into the volume. And again, we don't want m over here, I kind of forgot about that. We'll have to write this as rho into h2 minus h1. Of course, there's nothing wrong in writing the equation entirely in terms of the energies themselves instead of energy per unit volume, but I just prefer this form of the equation because you get an expression that is entirely independent of the volume. That is, you get an expression that is only a pressure, which actually proves pretty useful when you're solving problems and things like that. So we can write v over here plus rho v into v2 square minus v1 square plus rho v into h2 minus h1 is equal to 0. Alright, So I'm going to cut this, I'm going to cut this, and I'm going to cut this. So what you actually end up writing is P2 plus rho V2 square plus rho G H2 is equal to P1 plus rho V1 square plus rho G H1. And if you'll see, these terms are just merely placeholders. Yeah, like we're just talking about, say, one specific point over here and one specific point over here. In general, we can choose any point along this tube and derive the same thing. So what this actually means is, if we just remove the subscripts, we can simply see that the pressure at any point within a tube and plus the kinetic energy at any point within the tube per unit volume and the gravitational potential energy with respect to some particular point per unit volume is a constant. That is, we're going to call it K. It actually doesn't matter, just a constant. So this is actually Bernoulli's equation, and I think this video has already gotten quite long. So we're just going to end this video over here, and I'm going to talk about its various applications, things like Torricelli flow or Magnus effect, and even Pascal's law, and how Pascal's law is actually hidden within this equation. So see you in the next video, and thanks for watching.